Hi everyone. In this video, we're going to look at building a classifier, finally building a classifier, a k-nearest neighbor classifier using scikit-learn. Before we get started with this, I just want to spend a few minutes talking about classifiers in general, and I'm going to start that discussion with talking about labeled data. What labeled data is that each instance, we might have 100 instances in a very tiny learning data set, thousands, tens of thousands of instances, but each instance has a label, what we're trying to predict, and a set of features. So we have a set of features, a label for each instance in our data. So this is a data set of diabetes. We're trying to predict whether someone got diabetes or not, that number 9 on the list. And each instance will be labeled. Yes, this person got it, this person not, because we need something to start learning. So here's an example of someone who got it, here's someone who didn't, and we're trying to learn, well, what features are important. So we have that label, and we also have those 8 features, how many times the woman was pregnant, what the plasma glucose concentration was, and all those other features. A recent COVID data set looks like this, where we're trying to learn whether someone ended up in the ICU or not. So each instance is labeled. Yes, this person got in the ICU, this person didn't, as well as the features of that person, what their sex was, their age, were they pregnant or not, did they have diabetes, did they have some sort of pulmonary disease, and so on. So we have a set of features, and then we are told whether they ended up in the ICU. This is something we want to eventually predict. So the data set will look a little bit like this, where we have rows of data, maybe thousands of rows. Each row has a label. In this case, the label is the last element on that spreadsheet, but it doesn't need to be. It just happens to be in this case. And then we have a set of features, right? So we have labeled data. Here's another example. These are pictures. So the features in this case would be 3,000 pixels by 2,000 pixels wide. And each pixel has the RGB values, so it's 3000 by 2000 by 3. Those are the features, so the pixels of the picture. And the label we're trying to learn is, well, this is an instance of a dog. Here's a picture of a dog. Please learn when I show you another picture. Hopefully you'll be able to identify dogs. And the data set also contains cats. So here are pictures of cats. Features are the pixels. The label is cat. So that's labeled data. So we're going to have thousands and thousands of pictures of dogs and cats. Each one is the picture, and then the label is, this is a dog, this is a cat. And we use these when we're building a classifier, and let me explain how this would work. So initially we build a classifier. We say, hey, give me a k-nearest neighbor classifier. Then we're going to do some training. In sklearn, scikit-learn, this is called fit. We're going to take that labeled data. Here are pixels, and we're calling this one a dog. Here are pixels, we call this one also a dog, and now we call this one a cat, and so on. So we're giving these features and labels to the classifier, and the classifier is going to learn something. So it's going to learn how to identify these dogs and cats. So at the end of training, we have a trained classifier. It's learned what it can from the data. And then we give it a picture, for example, and it'll say, hey, this is a dog. Another picture, this is a cat. This is another dog, and so on. So once we train a classifier, we can use it to make predictions about unlabeled data. One way of looking at classifiers is if they're lazy or eager. These are terms that people actually use in the field. Most classifiers are eager learners. I'll start with talking about lazy learners. A lazy learner works like this, where we're giving a training set to the classifier, and the classifier just remembers each instance of that training set. So we give it 10,000 instances of these are gymnasts and basketball players and whatever else, and it just remembers them. It has 10,000 instances built into that classifier. Then it can use those when we're given a new instance. Hey, here's someone who's 50 inches tall, who weighs 96 pounds. What sport does that person play? That person's a gymnast, it'll predict. So it's just comparing that new instance with all the instances that are inside the classifier. And as you can imagine, this is how K nearest neighbor is. K nearest neighbor is a lazy learner. It just remembers everything. And then when we want to go ahead and predict something, it finds the nearest neighbor. It looks through that entire memorized list and finds here are the 5 nearest neighbors to this 50-inch, 96-pound person. And most of those people were gymnasts, so I'm going to say gymnast. That's a lazy learner. You can imagine that training then is super fast. It just needs to remember all the instances in the training data. This prediction or classification phase is slow. So we're given a new instance. It has to go through all those remembered instances to see which ones are closest. So that's extremely slow prediction. Eager learners are different. This is how eager learners work. They build a model. They're given a training set, and they're trying to extract some information from that training set. So in the top example, it's trying to build that line, right? That linear classification line. We have the y-axis being height, the x-axis being weight, and we're trying to build this line. Anything below the line will classify as a gymnast. Above the line will classify as a basketball player. So that's what an eager learner is. It's trying to extract some information from that data set, from that labeled data, and create some sort of model of it, in this case a linear model. Or maybe it's trying to extract some good questions to ask. Is this person's height below 62 inches? Is this person who's above 62 inches heavier than, 140 or whatever? It's trying to construct a set of questions. All of these are forming models, right? In one case it's creating a linear model, a linear representation. Another, it's a set of questions, but it's an extraction, it's an abstraction of the data set. So once it learned that, once it processed that training set, it can forget everything. It doesn't remember anything about a 48-inch person that weighs 87 pounds. It forgot all that training data. That information is represented in this model. Then the model is used to make classification, to make predictions of new instances. Here we have a 56-inch person who's 87 pounds. That linear model just looks at, hey, is it above or below this line? If it is, I'm going to classify it as a gymnast. The decision tree, the one that asks questions, might say, is this person's height below 62? Yes, it is. I'll label it a gymnast. In all these cases, we've seen that there are kind of roughly 3 steps in creating a classifier. One is that we create it. We just say, hey, give me a k-nearest neighbor classifier. The second one is we train that classifier on some labeled data. Once we train that classifier, we can then use it to make predictions on unlabeled data. Once we train a classifier to recognize what an image is, we can just feed it a bunch of images that are unlabeled, and it'll say dog, cat, giraffe, whatever. So those are the steps involved. And one question we might ask when we construct this classifier, though, is, well, how good is this classifier? And what we're going to use here is accuracy. How accurate is this classifier? And we're going to define accuracy as its standard definition, which is what percent did the classifier get right? So if the classifier looked at 100 instances and got 90 of them right, well, that classifier would be 90% accurate. So that's what we mean by accuracy. And so we can kind of say, hey, this classifier is good because it got an accuracy of 99%. So in illustrating this, let's go back to an example we saw much earlier. In looking at the label is X or not X. And I'm giving you a set of labeled data. That's what we started with, labeled data. So I said an elephant's an X. A giraffe is a non-X. My poodles are an X. Poodles in general are an X. And deer are a non-X. So you're to take these training examples, somehow build a model or build some sort of representation or just remember them. And based on them, you're going to be predicting if an animal is an X or non-X. So we're going to try to determine how good are you? What's your accuracy? And here's the test. I ask you, what about an elephant? What about a giraffe? What about some poodles? And I'm thinking that if your memory is pretty good, you're going to be 100% accurate on that test. So we can say, hey, you learned about X and non-X at 100% accurate. And the question then would be, well, is this really an accurate reflection of what you learned? Did you really learn what an X is and what a non-X is? And I'm hoping you'll say, well, no, maybe I don't know what an X or non-X is. I was just really good at memorizing all those examples and regurgitating them back. You showed me an elephant and you said it was an X, and I just remembered that. So that's really not a good, accurate representation of how accurate you are in deciding X or non-X. The problem was, when I was testing you, I used the same data that I used to train you, to train a classifier. So that seems like, well, maybe that's a mistake. So what I should probably do is I should check with animals you haven't seen, right? So I want to check how good you are in determining X and non-X by stuff you haven't seen before. So I can ask about this parrot we haven't seen, this mountain lion, do you think it's an X or non-X? This goat, is it an X or non-X? And based on that, based on things we haven't seen, I can say, well, maybe you're 33% accurate. Maybe you weren't perfect. Maybe you remembered what an X and non-X was, so you're just good at it. So the key here is we shouldn't test accuracy with the data we trained on, right? Because you can just remember it. It gives us kind of a false sense of how accurate, hey, I'm 100% accurate, when that's not really an accurate representation. So I'm using accurate in two different ways here, but that's not a really good way of determining accuracy. We should always test on new information. So it would work like this, where we would have this data set, let's say of images and their labels of dogs and cats, and then we'd divide it up. We'd have a training data set and a testing data set. Let's say we put 80% of our data in the training data set and 20% in the testing data set. So that's what we do. And then during training, when we're fitting in the sklearn terminology, this classifier, we'll use the training data set, right? So the features and labels of the training data set, that 80% of the data, let's say. And then when we're trying to determine accuracy to see how good is this classifier, we're going to use it to predict things. We have the test data set, the features of them, and the classifier makes some predictions, dog, dog, cat, dog, whatever, through the whole list of images. So we have the predicted labels, then we know the actual labels because it's labeled data. And based on those two, we can compare those two and determine accuracy. And this will be a much more accurate, I'm trying to think of other words to use other than accurate, an accurate prediction or assessment of how well we did with our classifier. So that's kind of the grand scheme, that we shouldn't test with the training data. So that's pretty much it for this really short video, just kind of getting a brief outline of what the larger, higher picture looks like. Let's get started actually coding. Thanks.